All right, the 2024 AP Chem free response has been released, and I'm gonna do my best to go through question 1 of this free response. No guarantees on anything, but I'm gonna try my best. So the first question is about a reaction between lactic acid and sodium hydroxide. It's an acid-base reaction, and it shows the structural formula and asks for this, the circle the hydrogen atom most readily participates in the chemical reaction with sodium hydroxide. So if you know about acids, this is a carboxylic acid. The carboxyl group is this area right here. So COOH. It's also seen in acetic acid, which is a common acid that we use. And this H right here, that is the one that reacts. If you know about hydrogens and acids and everything, none of these other ones are gonna react ever. The only other one that you might think about is, oh, OH is here, but this is the carboxyl group, so that's the acid H right there. So that's probably a point. Student begins experiment by dissolving 10.22 grams of sodium hydroxide. It gives you the molar mass, enough water to produce 500 milliliters of solution. Calculate the molarity. So this one requires that you know what molarity is. If you take in all of AP Chemistry, you hopefully know molarity is moles divided by liters, and you have your 10.22 grams. I tell my students, anytime you see grams of anything, change it to moles, okay? You're gonna have to have moles of something in there, and they give you the molar mass here. So I first change this to moles. So I go 10.22 grams, convert 40 grams per mole, that's 0.256 or 2.55 moles of NaOH. Once I have the moles, I'm gonna divide it by liters. They give you this in milliliters. So you gotta know that there's 1,000 milliliters in a liter. Change that to liters, and you have 0.2555 moles divided by the 0.5 milliliters, and that's 0.511 molar. Okay. Part C. Let's just start looking at graphs. Okay, so this one here, student uses, so this is a titration curve, uses sodium hydroxide from a burette, pH meter, a flask, to titrate a 25 milliliter sample of the acid. And this is very similar to the 2022 question. So I was talking about that with my students too. Hopefully y'all got this question. Approximate the pKa of the lactic acid. So the pKa happens at the half equivalence point. The half equivalence point is half of the equivalence point, of course. So where's the equivalence point? This is the equivalence point here. This is 16. It's the point where the inflection is the steepest, and so halfway is going to be half of that. So look at half the volume. That's 8, and that's going to be up here. So I would say the pKa is about 4 or maybe 3.9 on here. This is 2, this is 3, it's right around, so I would say 3.9-ish, okay? That might get you the answer. Okay, the next part here. So the preceding diagram represents relative amounts of major species in the solution. At one point in the titration, no water molecules. Draw an X on the preceding titration curve showing where the reaction mixture would be best represented by this diagram. So this is a couple of things you gotta know. You gotta know this is the acid, and this is the conjugate. So I have my acid here, my conjugate here, and what you have to know is at the half equivalence point, I'll zoom in here, the half equivalence point, back where we talked about, the concentration of acid equals concentration of the conjugate. Okay, so at the half equivalence, they're equal. Here, at the beginning, it's all acid. And here, it's all conjugate. Oh, you can't see that hardly. So at the equivalence point, it's all conjugate. Beginning, it's all acid. Because I have more acid than I have conjugate, that means it is before the half equivalence point. So anywhere in here, except for here, I would say your best bet is you just put an X right here somewhere, okay? That's gonna be before the half equivalence point, and then to justify it, you just kind of say what I just said. I wrote down something like, at the half equivalence point, these are equal concentrations. Before the half equivalence point, there's still more acid that's not been reacted with the OH minus, because the OH minus is changing the acid to its conjugate. So since the picture has more acid, we talk about that picture, it's gotta be before the half equivalence point. All right, next part. Student repeats the experiment using a solution of NaOH twice the concentration as shown in the preceding table. Once again, very similar to 2022. Except they used a different acid in that question. On the following graph, draw the titration curve that will be expected here. So this is my double concentration. This is the double the mass, but same here. So if it's double the concentration, that means it's gonna react twice as fast. So this is experiment 1. They gave you lots of space to do this just in case you didn't know what to do. Double the concentration means it's gonna react in half the time. So that means your equivalence point is gonna be around here. Okay, so I would go ahead and draw something like this, and then probably gonna go up like this, and then over like this. So that is gonna happen twice as fast. Now, if this concentration was half of it, it would take twice as long, then it would be out here somewhere, you know, way out by 32. So 16 milliliters, it would take 32. But since it's going faster, 16 cut in half, 8 milliliters. Okay, so this part here, student investigates the enthalpy of a reaction between acid and sodium hydroxide, 100 milliliters of 0.5 molar lactic acid at 20 Celsius, and 100 milliliters of 0.5 molar NaOH. So we have equal moles of things, important to know. Final temperature is 23.2. Assuming the density is 1 gram per milliliter, assume and specific heat capacity, calculate the Q. Okay, so this one, you gotta know a couple things. We have our equation, Q equals mc delta T. And it's on the equation sheet, but you should know that this is heat produced. M is mass. They give you volumes here, but they tell you that the density is 1 gram per milliliter. So if I have 200 milliliters, that means I have 200 grams. So you gotta know that. C they give you, and the change in temperature is the final temperature minus initial temperature. So I went ahead and did all my mass is 200 grams. I'm gonna write that down. Delta T is my 23.2 minus 20. So that's 3.2 degrees Celsius. And my Q solution is gonna be M times C times delta T, which is 2688 or 2690 joules. Okay, next part, molar enthalpy. So it says now calculate the molar enthalpy. I'm always telling students, if you don't know how to do this, You know, if you look at the units, you can figure out a lot of things from the units. You got joules and we got moles. So if you want to calculate this, you need joules and you need moles. I always start with remembering, so this includes sign, right? So in every reaction, you know that there's a Q from the reaction and the Q from the solution, because that's just the Q that I measure. The Q is the reaction. We can't measure heat from reaction because it's very difficult to measure changing heats of things reacting, but I can measure the solution, and they equal 0 by the first law of thermodynamics. And so if I have a Q reaction, that means this Q reaction is going to be opposite of the Q solution, which is a negative number. Now, if you know the temperature is rising, it's an exothermic reaction. All exothermic reactions have to be negative. My Q is going to be, so I need moles now. Now the moles, what you have to know for this one is you got to know that, well, I'm just going to show you some stuff. Okay, so here we go. This is the reaction. This is from the first page of the problem. And this is a 1-to-1 ratio here. So 1-to-1 ratio, they also tell you that the molarity and the liters of each thing is the same. So if it's 100 milliliters or 0.1 liters and 0.5 molar, that means you have 0.05 moles of each thing reacting. So there's no limiting reactant here. They're both equal. And I know that that's the moles of reaction. So the moles of reaction are going to be 0.05 because I need to take the moles of one of the things. This is how much is reacting. And then I divide it out. So that gives me negative 53,800 joules, or in kilojoules, negative 53.8 kilojoules per mole. Okay, last problem. The student claims that heat's lost in the calorimeter. So there's air. The experimental value of the molar enthalpy will be smaller. Do you agree or disagree? I drew a picture for this one, kind of easier to understand. So you know that the reaction's happening here, and energy is going into a thermometer to make the temperature go up. Now, if some energy goes out, then we lose some of that energy. And if I lose some of that energy, that means this temperature does not go up as high. So if this temperature does not go up as high, then the student's correct. I just said, since some energy is lost to the air, solution temperature will not rise as much as it's shown. So always write about the things you're measuring, and then you write about the calculation. So this makes delta T less than what it should be. That makes Q smaller, and that'll make delta H smaller. So always write about what's measured, and then what's calculated. Okay, write about how those things, because you measure the temperature and you calculate the delta H. So there we go. That's problem 1. I'll try to do some of the other ones a little bit later.